We continue to explore embedded systems. We're going to start by looking at systems other than Linux. Because Linux is a general purpose operating system, it carries with it overhead that operating systems designed specifically for a particular function do not carry. Linux would not be a good choice for the real-time telemetry required by autonomous vehicles. BlackBerry's QNX Neutrino operating system is partnering with about 40 automakers, including Ford, Acura, Volkswagen, BMW, and Audi. Wind River's VxWorks is a real-time operating system that conforms with the ISO 26262 safety standard. Toshiba, Bosch, BMW, Ford, and Volkswagen are among the manufacturers using this OS. There are a multitude of embedded system operating systems available. Linux could perform as the central control unit of a system of various embedded devices. While some companies, like Tesla, run their own homebrew Linux distros, most rely on Automotive Grade Linux, or AGL. Its membership includes Audi, Ford, Honda, Mazda, Nissan, Mercedes, Suzuki, and the world's biggest automotive company, Toyota. There are advantages to embedded Linux. Embedded Linux is efficient and scalable. There's a large established base of open source tools and applications. There's a large established base of support for a multitude of devices like cameras, displays, network interfaces, and really most other devices that you would find for a general purpose operating system. Open source operating systems require no fee to use, and the large installed base of kernel and application code is debugged continuously by crowdsource. Linux gives us freedom. Now Linux is free under the GNU GPL. It gives you the freedom to run the program as you wish for any purpose, the freedom to study how the program works, and to change it so that it does your computing as you wish. It gives you the freedom to redistribute copies so that you can help your neighbor. It gives you the freedom to distribute copies of your modified versions to others. However, Linux operating systems designed specifically for embedded systems, such as the automotive grade Linux, can be extremely costly. The Raspberry Pi bootloader. The bootloader is a closed source bootloader from Broadcom. The output of the bootloader is not provided to the console. It executes on the GPU, and the output can be captured via the USB to UART TTL3 V3 cable, which is not provided. The bootloaders, or all bootloaders, initialize system controllers, like memory, graphics, and your I/O. It allocates protected memory space for the operating system. It finds the operating system and provides the actual loader. And then it loads the operating system and passes control to it. The closed-sourced Raspberry Pi bootloader from Broadcom is proprietary and can only be redistributed in binary form without modification, and it's only for use with a Raspberry Pi. The first user space. The last step in the boot process is to call systemd init, the first user space. The systemd system starts services in parallel reducing boot time. The system control command, systemctl, displays a list of all running services. The systemctl isolate and set default commands can be used to enable and disable services available at boot. Sudo systemctl isolate multi-user.target disables the graphical interface. Sudo systemctl isolate graphical.target enables the graphical interface. Sudo systemctl set default multi-user.target sets the Raspberry Pi to boot without the graphical interface, that is, into the headless mode. Managing Linux. So don't be bashful about using the man command, M-A-N. Before every command, you can type man and then a command, man mount, man df, man find, and it will give you help for those commands. Now, the super user. You don't want to be a super user. You want to be an ordinary user. And if you need to elevate your ordinary user privilege for some commands, then use sudo. Now, some of the file system commands you need to be familiar with are df for disk free. It lists the free disk space. Mount makes new storage devices active. Find locates a file in the file system. Where is locates a binary executable in the file system. More and less allow long messages, text, and logs, etc., to be paged for readability. Symbolic links are not going to be discussed in any detail during this session. And we're not going to pay a lot of attention to users and groups and file system permissions at this time. But we will talk about SD card reliability, because the SD cards that hold your boot or your operating system on your Raspberry Pis have a limited write life. So using an SD card with lots of extra space extends the SD card life via wear leveling. Now, the wear leveling algorithm allows the operating system to write or to uh, different locations, to the unused locations on your SD card. So instead of writing to the same area of the SD card over and over again, wearing that area out quickly, the wear leveling algorithm allows writing to the unused portions. So as an example, if you were using a 32 gigabyte SD card with an 8 gigabyte operating system, the wear leveling algorithm could, by using the unused space to write in, could extend the lifetime of your SD card up to perhaps 4 times. We'll finish off our Linux commands with the diff, uh, tar, and md5 sum commands. Diff displays the difference between two files. Tar is used to combine files into a single file, which could be compressed like a zip file. mdsum allows you to check the hash of a file to make sure that it hasn't been corrupted or changed in some malicious manner. Controlling Linux processes. PS, the command PS displays running user processes and their PID, their process identification. PSAX displays all running processes. Foreground processes occupy the user space, and background processes could continue to execute while the user utilizes the foreground space. The kill command is used to stop a running process uh, by using the PID. Kill and the PID will stop that process. That concludes today's episode, and we'll pick up the next session with creating a repository using Git.